Okay, we are at uh, 18.3. I think it is magnetic fields, and my cat wants to be in on the video. Go on, go on. Um, let's share the PowerPoint. Now, if a charge is in a static magnetic field, there's no effect on it. But if a charge is moving in a magnetic field, it's going to experience a force, and the force can be determined by the force is equal to the charge, however many coulombs it is, times the velocity of the particle, times the magnetic field, times the sine of theta. The uh, the magnetic field and the um, the direction of the particle relative to the magnetic field. Uh, if so, the sine of zero, if uh, the sine of zero is uh, zero. So if the particle is moving along the magnetic field, there is no force. If it's moving perpendicular to the field, it's it's maximum. So force is equal to QVB sine theta. Now, from this, we can define a magnetic field. So B, the magnetic field, is defined as the force on the particle divided by QV sine theta. So force is in newtons, Q is in coulombs, V is in meters per second. We'll see that we define that as Tesla or Webers per meter squared, but you can see that besides Tesla and Webers per meter squared, we had newtons over coulombs times meters per second. Just look at it. Look, the F is in newtons, Q is in coulombs, velocity is meters per second. The sine of theta is unitless. It varies from -1 to 1. And since coulombs per second is amps, we can also define it as Newton amp meters. So that's how we define the magnetic field. Uh, Tesla is what we use in this SI system of units. There is the CGS system of units, and even though we don't use many units from the CGS, we still use Gauss. As a matter of fact, most of the time, if you have a instrument that measures magnetic field, it's called a Gauss meter. Some people may call it a Tesla meter, but most people call it a Gauss meter. Um, the uh, so I forget what the Earth's magnetic field. I think it's in. Uh, I won't say it because I don't want to be wrong. Okay, so the for F max, it's just the sine of 90 would be 1. So it's going to either go from -1 to 1. Sine of theta is going to go from -1 to 1. So the uh, when it's 1, it's at maximum, and it's F max equals QVB. It's just QVB. Let's see. So that's, of course, it's 0. F is 0 if it's 0 if theta is 0 or theta is 180. So if this is your magnetic field and you're going like this, you have no force. But if you're going perpendicular, that's when you get max. Now here's the force. The magnetic force is perpendicular to both V and B. So whatever plane determines the B field, the magnetic field, and the velocity, the force is perpendicular to it. The magnetic forces on oppositely charged particles moving at the same velocity in the magnetic field are in opposite directions. Now, they have a right-hand rule I'm not going to spend much time on it because I don't particularly care for this right-hand rule. I'm going to show you another right-hand rule, and I need to switch to the iPad. I like this one much better. Here we go. And this is the one they show you in your book. I get this out of the 24-26 physics book. I like their use of the right-hand rule better. It's easier for me to discuss and talk about. So let's see if I can zoom this and just ignore that. Just ignore the A part. Okay, let's say you have a magnetic field. Your fingers are in the magnetic field, the direction of the magnetic field. Your thumb is in the velocity of the particle. Now, if it's a positive particle, think of the palm of your hand, positive. If it's a positive particle, the force is perpendicular to the palm of your hand. Now, notice that the velocity can vary. It doesn't have to be 90 degrees. It could be like 30 degrees or 60 degrees. It doesn't have to be 90 degrees, but as long as you have a B field and you have a velocity that's not 0 or 180, that defines a plane, and there's a force that's perpendicular to the plane that makes up the B field and the velocity vector. Now, if it's a negative particle, I don't have a mnemonic for doing that, but just positive, palm, positive. If it's negative, it's towards the force is towards the back of your hand. I like this right-hand rule better. We'll do a few exercises in class to help you remember this right-hand rule. I like this right-hand rule much better than this one, so just kind of ignore that one. We'll stick with this one, and I'll post these auxiliary notes at the end of the module. Okay, I think that does it for the I think that does it for yes, that does it for the for this section.